Hello, good day. My name is PAVEL, master degree student at the Durango Technological Institute. First, I'd like to greet the Cier 2025 Congress for the space created to promote scientific divulgation in Mexico, especially with the youths. We, the youths, are really committed to the scientific community, and this kind of digital platforms give us the opportunity to enact our academic investigation to the world. Today, I'm here to present an investigation titled Design of Solar Concentrators for Thermal-Solar Performance, a New Approach. Through this presentation, we'll explore an introduction to the fundamental theoretical work that inspired the design methodology. Afterwards, the methodology section will combine mathematical exactness with philosophical logical rigor of insight adduction concepts of thermal-solar energy flow. The results derived from an observational analysis of two low-temperature solar concentrators built with the design methodology. The observational data was obtained through the ARELLANO 2003 normativity of standard test procedures for liquid heaters. Annexes will reinforce the conclusion that the methodological approach here presented designs solar concentrators that does not require solar tracking. Roland Winston, inventor of the compound parabolic concentrator, stated that it is plausible to optimize thermal solar performance if we pay less attention to imaging optic requirements. According to Roland Winston, in the most essential sense, thermal solar performance is comparable to writing a letter, putting it inside a box, and sending it from one side to another. There are two ways this message can be delivered. The first one consists of writing a perfectly coherent and well-cohesive message. The second consists of putting all the letters inside the box, no matter the order of the letters, and just taking the box from one side to the other. This is the main difference between imaging and non-imaging concentrators. When I got in touch with this text, at the same time I was studying coordinated systems to design solar concentrators. The concept of a CPC, seen as a black box, was presented to me. These thoughts brought to mind that the flow of thermosolar energy from the plates to the receptor could be simplified by differential calculus. In practice, solar tracking requires continuous movement mechanisms of heavy structures for long periods of time. Due to deterioration of those mechanisms, catastrophic failures lead to fire incidents. The objective of this research is to analyze the type of use and functionality of two solar concentrators as built using data obtained from ARELLANO 2003 normativity of standard test procedures for liquid heaters in an observational analysis performed in Minitab statistical software. According to S. Tapia and J. A. Del Rio, there are 5 parameters that must be considered to design a solar concentrator: focal length, acceptance angle, receptor area, aperture area, and height. 3 variables must be taken as dependent and 2 as independent. This is where the new approach begins. It is not common practice to take focal length and acceptance angle as 2 independent variables. However, this is where the insight abduction concept of the black box takes place. Winston's theoretical maximum concentration ratio stipulates that rays emerge at a unitary ratio of P divided by 2, equivalent to 45 degrees. Therefore, acceptance angle as a maximum concentration ratio was set to 45 degrees. The focal length is defined by this equation, where the receptor area A' is solved by this other equation, with all the geometric properties of the receptor. After this, part of the procedure of description for a compound parabolic concentrator in a Cartesian system provided by S. Tapia and J. A. Del Rio as a graphical method was followed. In subsection C, we have a complete description of a parabola of the form 4 times focal length times z1 equal x to the power of 2 on a Cartesian system. A translation of the coordinated axis takes place to generate a function which represents the parabola tilted at the Cartesian system. This can be visualized in subsection A. However, remembering the laws of calculus, all functions must be continuous. Therefore, these authors solve the implicit quadratic analytic expression with a linear term of coefficient distinct from zero for C1b' and C2b'. These equations can be visualized in subsection B. Now, this is a relevant part of the graphic method. The corresponding axis of intersection corresponds to the segment BQ shown in subsection C. This is an excellent point for a designing parenthesis. This intersection will move depending on the shape of the concentrator, but if the expression does not intersect the axis, it means the thermosolar energy won't flow to the receptor. It becomes easy deduction that from here, a metric value of the dependent variable A' can be defined by solving this equation, and the aperture area can be defined with this other equation, and the height can be defined by this equation, where phi will be taken as 90 degrees for all cases. Height can be adjusted to fit the length of the plate. With only one last data missing, the length curve theory is applied. When applied this equation, the intervals of the functions that describe the relative variations of the variables involved when obeying the law of reflection of light are the aperture area and the receptor area, or as seen in the previous slide, segments of a Cartesian system. Allow me to show you the results. This methodology was applied to build two solar concentrators, and these are the concentration gaps between the theoretical concentration ratio and the practical for the first concentrator, and the theoretical concentration ratio to the practical concentration ratio of the second concentrator. The shortening of the practical concentration ratio and theoretical concentration ratio has already been accomplished, and it can be found in the industry with the parabolic mirror. However, this is solar tracking dependent. This gap was the first indicator that solar tracking may not be required. Here is the first observational analysis performed at the first concentrator designed. The thermal images here were taken using an uncooled infrared local plane thermal imaging sensor camera model Unity UT20S. Observe these three pictures, one from the receptor, another from the whole plate, and the third one closer to the reflective area. The concentration ratio, remember, is unitary, as the gap from the theoretical concentration ratio is 0.4. Pay attention to the temperature equilibrium. When radiation is as normal as possible, reflective area at 41 Celsius degrees and fluid temperature at 41 Celsius degrees. This is a physical observation of a thermodynamic phenomenon known as the ellipsoid paradox in thermodynamics. This phenomenon confronts real-life situations with a thermodynamic view. In the simple sense, when both objects start at the same temperature, thus objects being A and B, present an efficient radiation transfer in equilibrium, and the form of the designed concentrator does not converge to the ellipse sphere configuration. Notice both objects, A as the fluid in the receptor and B as the sun radiation emitted, have the same temperature. Now that the flow of thermal solar energy has been proved, an observational study was performed using a factorial design since times 5, two study factors, hour and position, temperature of the fluid as response variables, and covariables suggested by the normativity as right answer 93 2003. Covariables will be shown in the annexed section. The positions of this analysis were calculated to determine solar tracking angles of surface according to the system of equations provided by John Duffy. Position A, azimuth tracking and zenith angles equal to inclination beta by hour of use. Position B, azimuth tracking and fixed inclination beta. Position C, azimuth fixed south and fixed inclination beta. This is the full fixed position of the concentrator. And position D, azimuth tracking and inclination as theta equal tangent of beta. With the data gathered, a critical region punctual estimator F was used to observe a non-significant difference between the 5 position tested. After this conclusion, the second concentrator was analyzed with a fixed position south and normal to Earth axis, with a factorial design 11 times 6, 2 study factors, day and hour. Temperature once more as the response variable and covariable suggested by the normativity as right answer 93 2003. Covariables will be shown in the annexed section. The critical estimator F test evidenced that there is a significant difference between the temperature means increase due to the hour of use. A new question arises: how to be sure that this significant difference is only due to the radiation variations during the day? Let's clarify this question in the annexes. Castellanos 2025, through the similar variables analysis approach, a permutation future importance method concludes that direct normal irradiation is the most important factor, and temperature and wind velocity have not great importance. This author attributes the low importance of temperature to thermal inertia, which can be described as the capacity of a system to retain heat instead of losing it to the environment. When using the right answer 93 2003 normativity, the product gain-loss evaluates the thermal behavior of solar concentrators as built, in one hand, by measuring thermosolar energy transfer to the fluid, in the other hand, measuring the amount of heat lost to the environment. With this in mind, it is accurate to say that variables such as wind, velocity, humidity, variation of ambient temperature, heat losses by conductions, variations of the acceptance angles, and variation of solar radiation during the day caused by clouding and shadowing are taken into account in this product gain loss. In subsection C, for the same concentrator, meaning concentrator number 2, a notable hourly difference of this product is observable. However, is this difference significant to the temperature of the fluid? An Fmax test for this parameter was performed, and there is non-significant difference between the means of the temperature due to the product gain loss. At the same time, in subsection B, efficiency looks consistent during the hourly performance, despite the few variations in optical efficiency. This reinforces the conclusion that fixed use is adequate and the temperature is mostly influenced only by radiation during the performance. In subsection A, optical efficiency parameter for this first concentrator reinforces the fixed use in a more notable way. Optical efficiency is almost the same between the fixed use and the solar tracking. Here are the ANOVA tables of both concentrators. At the left side, the ANOVA table for concentrator of unitary radio of concentration, and at the right side, the ANOVA table for concentrator of 1.46. That is the data gathered for the statistical observational analysis. The methodological approach exposed shows a remarkable benefit for designing solar concentrators. All the designers need to do is provide the desired concentration radio, the receptor geometry available, and the rest of the variables are clear by equations, graphic methods, and the long core theory applied. At the same time, the observable decrement of the concentration ratio will guide the designer through the temperature expectations before fabricating the concentrator. At last, this photograph shows with total clarity the airy disk at the focal length. Airy disk is the pattern of diffraction of light when best focused at a spot. To conclude, Madala 2017 discussed designs of several solar concentrators include CPC, truncated CPC, COPS concentrations, Prim's couple, CPC, CCAC, CEC, DCPC, CTIRC, DIA-CPC, CH, trumpet-shaped concentrator, polygonal profile concentrator, B-toed profile concentrators, TRCS, non-imaging Fresnel lens, two-stage and multi-stage non-imaging concentrators, and none of these are similar in design methodology to the one here presented. So here it is, a new approach to design a non-imaging concentrator. References are quite simple but very powerful. The fundamental theoretical work of Roland Wiston, the Mexican touch with S. Tapia and J. L. Del Rio for the methodology, the international touch with J. A. Duffy, and the calculus theory applied with Ruben Flores, the statistical designs with Humberto Gutierrez, P. Roman, and Robert L. Manson, and Castellano Garcia with a comparative of the variables described, and Madala 2017 to compare 16 different designs of solar concentrator with the one here presented. Thanks for your time. This is the end of the presentation. Greetings from Durango, Mexico.